session of this Congress. The title is Energy and Environment, identified by green color. And before we start the speakers and the professors to present their talks, I'd like to invite our scientific panel to the stage. Professor Mushfaq, please. Professor Sabah. Assistant Professor Fattah, Dr. Fattah. Dr. Zvani. And Professor Kurabos, please. Dr. Fattah is not here. I think he will join us shortly. All right. The next speaker is Dr. Mojtaba Abdi-Jalebi. He is an associate professor from University College, London, UK, and the title is Advanced Scalable Coatings for Next Generation Green Energy Devices. Please welcome Dr. Jalebi.
First of all, I would like to thank Professor Chini for the kind invitation, and Professor Sabah, and all the executive and scientific community of this conference for all the efforts behind this conference in beautiful Kish Island in Persian Gulf. So, I'm Mojtaba Abdi-Jalebi. I'm associate professor at UCL, University College London, and I'm the head of functional energy devices materials and energy devices at Institute for Material Discovery. So during this talk, I'll briefly introduce myself as well as our university. Then I'll talk about emerging energy harvesting and storage devices. And I'll give two case studies where we are utilizing advanced scalable coating techniques for our energy devices. One is on perovskite photovoltaics. Second one is on electrochemical devices for CO2 reduction. Right, so UCL, or University College London, is one of the top universities in the world. So it's ranked 4th in the Europe and UK and 8th in the world. And it has 11 academic faculties and over 43,000 students. And it's ranked first in the UK as per the quality of the research. And it's well connected across the world, so we have over 50% international students and 34% international staff. In terms of location, UCL is located in the heart of London, so it's very close to the British Museum, and it's very sort of central in London. And this is our new campus in the east side of London, so we had our largest expansion in the past 200 years of our university history. So about our institute, it's called Institute for Material Discovery. So we also located in both sites, in central and also in the east side, and we offer 5 master programs ranging from advanced material science to energy storage, sustainability, innovation and enterprise, as well as the data-driven material science. And we are doing a wide range of research. It's a dynamic world-class research from the energy sector to data-driven material science. So you can see a number of sort of case studies in this slide. In my research group, we focus on developing both materials and devices to address a couple of global challenges, including clean and affordable energy resource, as well as like the clean water. In particular, we focus on material discovery, synthesis and coating and characterization, and making optoelectronic devices is one side of our research activities, and the second part is on developing devices to generate green fuels. In more detail, so basically the materials that you can see in the center of this sort of slide, it's called so-called perovskite. I'm going to explain about it shortly. And then you can see that it has a lot of applications ranging from LEDs to solar cells to detectors. This is the same material, we are just tuning its dimensionality and also its sort of composition. And we also utilize different materials, nanomaterials and layered hydroxide materials for catalysis application as well as CO2 reduction, as you can see. And we are trying to combine both photovoltaic and the electrochemical system to make a fully sort of sustainable system for production of green fuels. And recently we have done this project called ICCC. I'm going to give you more details about it, but this is in line with the carbon circular economy, which is at the moment has a huge impact against the energy crisis that we have. Right, so this is a famous plot that I normally show in my presentation to shows the impact of our work. So basically this is a simple chart that shows the temperature rise from pre-industrial sort of era until now. And you can see we had a huge temperature rise from 1960. And if we don't do anything, this will go above 1.5 degree increase in temperature, which is like a critical point. If you pass this point, there's no, there will be a lot of catastrophic events that will happen in the world that are sort of not reversible. So it needs a huge global efforts to prevent that. And these are some sort of examples of what will happen if you don't do anything and sort of be past the critical temperature rise point. Right, in terms of solution, I think Professor Moshfegh yesterday explained very nicely that renewable energies are one of the best solutions that we have at the moment. And among all the renewable resources, you can see the capacity of solar is by far the most abundant resource that we have. On the other hand, the capacity of usage of solar is very subtle. So you can see the current photovoltaic installation back in 2022 is 1.2 terawatts, while we have the capacity of 200,000 terawatts. So you can see we are just using a very small portion of this huge abundant resource. And the other aspect is renewable energy is a great solution, but it's not the only solution. As you can imagine, we don't have sun all over the day or in the night, or also wind. We don't have wind everywhere in the world. So that means we need to have also other solutions against global warming and temperature rise. One of the other solutions is utilizing electrochemical system that can sort of utilize sort of split the water or convert the CO2, which is the main cause of global warming and temperature rise, into useful product that can be utilized. And this is also a major motivation for many industries to get involved actually to this global efforts of sustainable energy resources. So you can see that there are a lot of products that you can get from CO2 conversion, and some of them are very interesting because they have a huge market value. So if you produce them, so you can also profit, you gain profit. So this is a good motivation for industry to decarbonize their sort of production line. Back to solar photovoltaics. So you can see that the deployment of solar photovoltaic has been very interesting, especially in the past 5 to 10 years. The major sort of barrier against solar energy sort of global or widespread adoption is cost and efficiency. So in terms of cost, you can see over the past couple of decades, there's a huge reduction And in terms of performance, nowadays we are reaching a significant enhancement in the performance of solar cell, reaching over 30%. So these both are helping us to go even beyond the prediction in terms of PV adoption in our society and in the world. And this is also showing the cost of solar PV over the past decades versus the other energy resources like offshore wind or onshore wind. You can see solar has the most significant rapid reduction in the cost. And in some parts of the world, like in the Middle East area in UAE, the studies shows that solar energy is even cheaper than the conventional energy sources like coal and sort of oil. In terms of performance, there have been significant progress, especially with the utilization of a new material so-called perovskite. So recently, there's a record of over 74%. This is a huge gain in the efficiency compared to like 25 at the moment in the market. So you can see that the progress in both cost and efficiency is significant. And this might not be sufficient if you just go for typical solar farm. So we need to have integration of photovoltaic in many different parts of our society, including like utilizing photovoltaic for agriculture, which we call it agri-photovoltaic, or utilizing the floating photovoltaics so you can utilize them in the sea, in the Persian Gulf perhaps in the future, or road integrated PVs. In terms of new technologies, so there's one technology that shows a significant advantage over the past decade compared to other PV technologies. And the name of this technology is perovskite. So the typical or the current technology is silicon, that most of you have heard about it. The reason it's been there for many years is it's very efficient and it's also reliable. But on the other hand, it's thick, it's rigid, and it has a heavy, it's also limited efficiency cap. And the most sort of limiting factor is its production capacity. So if you want to have like 25 terawatts of silicon PV, it takes 170 years based on the current capacity we have. On the other hand, if you look at this chart, which is a famous chart in the PV community, that shows the progress of different PV technology over the years, and you can see one technology, which I bring this part of the table here, shows a significant progress, and over the past decade it's reached almost the same level as silicon, and now even there's a potential to surpass silicon sort of efficiency. And this is based on a simple material, as you can see here. So it's AD3, is so-called perovskite. Perovskite is not a new material, it's been there for many years, but the utilization in the optoelectronic, like solar cell application, it's new, so it's been there since 2009. And if you look at the production of silicon solar cell versus perovskite, you can see that the silicon has a very sort of high energy process generating with a lot of waste. And it includes a lot of steps if you want to go from sand to your wafer. And if you now compare this perovskite, you have very limited steps. So basically you have a few salts, you make a solution like an ink, and then you can do advanced coating like roll-to-roll manufacturing and make your solar cell. So using this technology, we don't have any limit on the production capacity. You can make as much as solar photovoltaic as you want in a very short time. And if you also compare in terms of the raw materials cost, the finished material cost, fabrication cost, in all cases, perovskite is showing a green light for market adoption. And also brings us some new applications, because with this technology you can also make colorful photovoltaic panels that you can also actually use as like a window in your buildings. That's been actually already included in some building in Germany or in Europe, in Asia as well. So on the other hand, there's a couple of limitations for this technology. One is the scalability, so how we can scale up this technology without reduction in the performance. The other aspect is the stability, so how we can make them that can last for many years, over 30 years. And lastly, how we can go even make it more efficient. So I recently published this opinion paper in Nanoscale Advanced Materials Journal, which I talk about the future of perovskite solar cells, and how I see the market sort of projection of this technology. So I would highly recommend to look at this. So as you can see here, the stability, performance, scalability, and sustainability are the factors that we need to look at if we want to bring this technology to the market level. So now from here, I'm going to show you a few of our work that we have done in my research group to address some of these challenges I mentioned earlier. So one of them was about the stability and the lifetime of this material. So this material, perovskite material, is sort of ionic material, so it has defects within the crystal structure. So to make it very simple, so I'll make a schematic over here for you. So this is showing very simply the grain structure of the perovskite, and this white circle are showing the defects within the crystal structure. And what we have done in this work is we implement an additive, so-called potassium halide or potassium iodide, where you can actually fill out all of these vacancies, this additional halide that you are putting into your system, and also lock them up at the interface. So in this case, so you can gain stability. And this is just to prove what I've just said. So this is experimental proof for our mechanism. So basically, this is a high-resolution TEM of the cross-sectional solar cell, and you can look at the grain structure cross-sectionally. And here we can sort of deconvolute the phases that before. And one major phase we found, in particular at the interface, is potassium bromide, which is our passivating phase at the interface. So this is a proof for our mechanism. And we also look at the distribution of the defect within the perovskite thin film. And this is a very advanced measurement technique called time-resolved photoemission microscopy, where you can locate the defects within your semiconductor. And you can see on the left-hand side, you see a lot of defects within the thin film. And when we passivate it, you minimize the number of defects, and you have less sort of green spotlight, or orangish spotlight. And also it shows better optoelectronic properties. So I know that this is perhaps a little more sort of specific in terms of the field of our audience, but this is in general is showing a better optoelectronic properties, especially luminescence property, when you have this passivation phase in your system. And obviously we make solar cell out of this material, this passivation material, and then we show that it's improved the performance quite significantly from 70 to over 21%. And in this work actually we look at different compositional of the perovskite and how that impacts on the performance and the stability of the material. And on a following work, what we have done is to understand what is the limitation factor for such in this semiconductor, which is mostly defects at the interfaces, especially at the surface. And this we are utilizing this PIMS technique where you can actually visually see where the defects are and then find out how to prevent deformation. And what we have done in this work is we sort of look at the AFM techniques and combine it with the PIMS, and then we locate the defects, and we found that they are mostly located at the grain boundaries. As you can see, this is the grain structure. You can see a lot of grains over here, and then these blue spots are the defects. Now let's talk about the scalability of this technology. We have one of the challenge, if we want to go to the larger scale of this technology, from lab scale to larger scale, is in terms of their lifetime on their operation. So basically, one of the challenges when you go to the high temperature, so you can imagine the real solar photovoltaics normally goes to high temperature like 50, even in some places like here, it can go up to 80 degrees, the temperature of the PV module. So that means that the material or the device we develop that needs to be stable at that high temperature. One of the sort of instability sort of origin is mostly coming from the layer, so-called the whole transport layer that we are using in these devices. And in this work, we focus how we can replace that material and utilize the polymer material that can sort of survive at high temperature. And here, for example, we use PTAA material, and that helps us to sort of make it stable. You can see that this is the stability, the performance over time. That's a measure of the stability of our solar cell. And it also works at a larger scale. So this is a sort of a module size devices, over 70% for 43 per centimeter. And another sort of challenge is the actual absorber material that sometimes degrade at high temperature. And one of the sort of approaches to make it stable is to utilize the 2D material. So you have heard about the 2D materials, that they are relatively stable. And in the perovskite as well, you can play this dimensionality and make a 2D material or mix 2D, 3D. However, there are some challenges. One is the solvent matching. So basically, if you want a 2D phase and 3D phase together, just to mention that 2D phase by itself is not very optoelectronic active, so you need to have mixed 2D, 3D. One challenge is solvent matching, the other one is seed crystal growth, where you have seeds on the top of your 3D and then have 2D on the top. And the other approach is hot press. In all of these, it's very difficult to preserve the crystal and the good crystal structure of the perovskite. On the other hand, so what we developed in this work that published last year in Advanced Functional Material, we actually put the seeds in the solution of the perovskite, in the precursor solution, where you basically form the 3D across the 2D in one go. So you don't need to form your 3D first and 2D, but you simultaneously form both 2D and 3D. And this actually helped us to make it a very robust thin film. You can see the SCM images over here, so you can see it's significantly better in terms of the size of the grain and also in terms of the stability of the material. And obviously we made solar cell and we got over 24% efficiency. In terms of the stability, you can just quickly, I think the quality is not great here, but you can see that the one without the 2D phase is degrading significantly over time after 150 days, but the one with the 2D phase, there is almost no change. Right, the other work we have done is to look at how we can scale up the material in terms of the coating and sort of the deposition. One of the layers which limits the sort of the scalability is the electron transport layer. So basically for a solar cell, you need two specific layers. So you have your absorber layer that is sandwiched between electron and hole transport layer. For the electron transporter is the layer that you normally need a very high temperature, like over 500 degrees. So basically in the past couple of years, we developed materials so based on tin oxide that can actually be prepared at low temperature. And in this work, we explain thoroughly about what processing techniques to use. And the other thing which is actually relevant to this community here is the range of coating technique you can use for perovskite solar cell. You can see that this technology is very versatile. So you can see many different coating techniques ranging from plate coating, you can see the schematic underneath as well, inkjet printing, screen printing, slot die coating, spray coating, and PVD, so like physical vapor deposition. It's very versatile. So obviously each of them has a limitation as benefit, and at the moment the technique that has been mostly market relevant is slot die coating, but obviously the other one has the potential as well. And recently I've started a collaboration with a company so-called Phoenix Solar in Hangzhou in China, where we develop a large-scale perovskite panel. So you can see the module over here with my picture inside it. So, and this is the 10K line of this perovskite technology. And we are using a slot die coating, industrial level lasers, as well as the VCD annealing, ALD technique. So the mass production tech line has a capacity of 100 megawatt production, and the cell size is 0.6 meter to 1.2 meters. So it's relatively large. So I'm going to show you the picture. So this is the solar panel that we fabricated in this company. You can see that this is an actual industry level, industry standard size of the panel. And you can see that what we have achieved so far, and these numbers are changing on a daily basis as per the optimization we are doing at this company. So you can see that at very large size, nowadays we can go even close to 20% efficiency, which is actually acceptable for industrialization of the technology. I'm going to show you a brief video that shows the process of fabrication of this large panel. I hope it's working for you as well. I stopped the sound to minimize the distraction, but I'm going to go a little bit higher. Right, so you can see that this is the sort of the size in the Duarte scale, and this is the PVD machine. Maybe I go a little bit further to here and to here. Yep, so you can see the whole production line. Right, so this is the starting point where you start with a transparent conductive oxide coated glass. Then you put it in the machine for doing the sputtering to do the ETL layer. Then once you deposit your electron transport layer, you go to the slot die machine, as you can see over here, where you deposit your perovskite layer, absorber layer. And then you anneal the perovskite using the BCD technique, vacuum, and then you do the scribing to make those small sub-panel, and then evaporation system to do other layers, HDL and the contact layer. And finally, an atomic layer deposition to finish the cell. And obviously, afterwards, you go to the characterization to see what is the performance of your cells. So basically, this is a module that these engineers have made and looking at their properties and basically, yes. So you can see that you put the modules under the solar simulator and sort of look at the performance. Right, so that's the end of the PV parts of my talk. I think I have a little bit more time to talk about the green fuels. So basically, in the green fuels, I'm going to specifically talk about Next CCUS project. So this is an EU-funded project. We started in 2021, so now we are almost finishing this project. So Next CCUS is standing for Next Generation of Electrochemical System for Sustainable Direct CO2 Capture and Utilization Storage as Clean Solar Fuel. So this is a nice chart that shows that CO2 is coming from different resources. It's coming from biogas plants, petrochemistry or energy-intensive industries, and then using our system, we can convert it to a useful product so-called methanol. And methanol can be used in many different industries as well. So if you can feed it back to petrochemistry to make further chemicals, or you can use for transportation or fuel cell to generate electricity, and the electricity goes back to our smart city. And you can see that the whole system, this system is powered by renewables like photovoltaic panel. So you can see the whole system is circular, so we call it circular carbon economy. And it's net zero or even negative emission, because we are getting CO2 from air and from these sort of energy-intensive industries. This is a huge consortium involving industries as well as academic institutions, including UCL as one of the major partners. And here what we do is we do direct CCUS, so basically we do CO2, we do the capture and convert. While it's a direct electrocatalytic CO2 reduction to green fuels. Obviously, there is a lot of chemistry involved here, which I will skip. The reason we choose methanol as our major product, because you can mix CO2, you can convert it to many different products. So methanol has a very huge potential. One of the advantages of methanol is it has a huge energy content from both volume perspective and also weight perspective. So you can see it's higher than the batteries, it's higher than the hydrogen as well. So this is the sweetest spot that your technology wants to be at the moment in terms of energy content. The other benefits of methanol, it has a huge market price. So you can see that the price for coal or for CO, for syngas is very low, while the price for methanol, for any products above this line is very industry sort of market, it's a profitable product. So this is another example about the energy content capacity of this, the methanol compared to the hydrogen and battery system. And the other aspect is the investment you require. If you want to, let's say from tomorrow go to methanol and remove all the other sort of fuels. So the infrastructure investment you need is 10 to 15 billion, while if you want to go for hydrogen, it's 3 trillion and battery is 1 trillion. So you can see it has a better in terms of less investment required, and it already has a huge market, so almost over 100 million tons. This number is a little bit And in terms of technology, so basically this is our schematic of the system we are developing. So you can see it's like a tubular system, and this is the anode and cathodes are separated by ion selective membrane, and we have this mesoscopic sort of a structure. And we are using some new material like Mexene to enhance the performance and also selectivity of CO2 conversion. In terms of the coating, we are mostly using electrode deposition. You can see that this is, again, there's a video here, I'll try to play it. But this is electrochemical electrode deposition of our electrodes that we are developing. So basically it's 50 square centimeter, and obviously we are still in the lab here. And you can see that the final product is also over here, so 50 square centimeter. We are going even higher at the moment. And in terms of performance, you can see that it's very stable compared to other commercial candidates, like as mentioned over here, like iridium oxide, for instance. And in terms of performance, I don't know if you can see the bubbles, but yes, it would be very hard. So this is our electrodes that we developed. And this is the scalable electrode we developed. So basically, we also characterize it to make sure the quality is good. So we characterize different parts of the large electrodes, and we look at their electrochemical property as well as the material property, looking at SC and XRD, and we found there's almost no difference between number 1 to number 5 sections of our large area deposition. And it's very stable electrode as well. After 500 hours, there's almost no change in the potential. Just last 2 slides. So basically, we also recently look at the life cycle assessment. So when we develop the technology, it's very important to look at its sustainability as well. So, and to do that, we normally look at the LCA of the technology. So you can see that the CO2 to methanol, the next CCS technology, we look at the social LCA and also environmental LCA. And you can see that in terms of global warming potential, our technology is outperforming the current technology with thermocatalytic that has already been commercialized. And the other aspect which is very important to look at is safety. So basically, whenever we develop any technology, we need to make sure there is no harm to the community. And you can see that in this work we explain what are the potential harms and how to prevent that from the step 1. So it's very important that we look at this aspect in terms of environmental sort of aspect as well as safety at the beginning when we develop the technology rather than at the end. And I skipped the conclusion because of the time. So we recently also launched a journal called Nanoscale and Advanced Materials. It's an open access and free of charge sort of journal. We have published 3 volumes so far. So you're very welcome to submit your work here to this journal. And at the end, I would like to thank my research group. As you can see over there, these are my group members. In particular, these guys are very active in the work that we have done so far. And all the collaborators across the world in the University of Cambridge, in China, in STU, in Phonics Solar Technology Company, and also the funding bodies like Horizon Europe, ACT, as well as EPSRC and Voice Institute. Thank you very much for the attention. Happy to take any questions.
Thank you, Dr. Abdi-Jalebi. Okay, our scientific panel, please.
Thank you very much. Excellent, excellent.
Thank you.
Great job. I have 2 questions.
Sure.
You using sputtering and ALD, atomic layer deposition, is it increase the cost? If you're using rolling, it may cheaper, yes, because you're dealing with the stability,
yes,
scalable, and those are triangle efficiency, price, and stability. Okay,
sure.
The corner of the triangle: stability, cost, and performance. Okay, so if you using ALD and sputtering, the cost will be increased. This is not contradicted with your purpose?
Sure, that's a very good question, Professor Mushraf. So in terms of, so as you mentioned, there's a triangle and there's always a compromise. So if you go for roll-to-roll, at the moment the performance will drop a lot. Obviously there's an advantage if you use roll-to-roll, you can use flexible substrate as well, but you lose the performance quite significantly. So I think it's about 20% versus if you use the normal rigid substrate, it's over 30%. On the other hand, so at the moment ALD and sputtering are well sort of established techniques. And so the company and the line I showed to you, it's actually the company is selling the 10K line. It's a relatively good price. So, and the cost of the final panel, as per this, the cost as per the calculations, it's 1/3 of the cost of the silicon panel at the moment. So although they're using ALD and sputters, but yeah, your point is correct. So in the future, I would also predict it will go to roll-to-roll, but there are still some progress need to be done that we can preserve the performance for the roll-to-roll process as well.
I'm sorry for the interruption, Dr. Factor. Will you join the panel, please?
The second question is on a technical question on using potassium passivation to increase stability. So is it, do we try to blocking the diffusion at the interface, yes, to increase the stability?
Yes.
Do I understand correctly?
Yeah, so the problem is perovskite is there is a movement of the ions, in particular the halides, like iodide and bromide that we are using. So they normally move within the crystal structure. So once we use potassium iodide, we are preventing the movement by making a new phase, so-called potassium bromide. And that potassium bromide is preventing the movement of the ion. So that's the sort of rationale why we are using it.
It's a good...
Yeah. Thank you for the questions.
Okay, thank you.
Any more questions? Okay, any questions from the audience? Thank you very much, Dr. Dr. Mushfiq is going to be please. Thank you, Dr. Abdi-Jalebi. Now our second speaker is Dr. Ruhullah Baghar Zadeh. He is Associate